Hi everyone, and welcome to this session, which will be about the new timber design features for the European market in Advanced Design 2024. So my name is Thibaut Frété. I'm a structural engineer at Gretec, working on product specification and validation. So together we will see our new design for spaced members, which can be either spaced columns or spaced beams. Then a new verification for beams with a notch on support, then the check for the compression perpendicular to the grain, and finally our improved optimization process based not only on the resistance and stability work ratio, but also on the deflection values. Starting with spaced members. So in advanced design, you will be able to define either spaced columns or spaced beams. And spaced columns will be made of 2, 3, or even 4 rectangular shafts that will be connected by packs or gussets. And the design rules are coming from Annex C from Eurocode 5 Part 1.1. So in advanced design, you will define the number of shafts, dimensions of each shaft, as well as the spacing between them. Because the spacing A has an impact on the behavior in one of the buckling planes, so it is not designed as a solid rectangle. Also used in the design is the distance between the connectors, as well as the type of connector. Packs or gussets, and they can be glued, nailed, or bolted. So of course you will find the corresponding parameters in advanced design. So of course, the design limitations are the same as in Annex C, meaning the columns are assumed as simply supported, and the design checks consist of the verification of the actual load carrying capacity, as well as the verification of the load on the connectors. Check the actual load carrying capacity. We compare the design compressive stress with the capacity of the column, which depends on the material characteristics, the class of service, load duration, as well as the buckling coefficients in each plane. So in one plane, there is no impact of the number of shafts or even the spacing between them. It's just like dealing with a solid rectangle. You compute a slenderness and a relative slenderness, a Y and a KC. But in the other plane, you have to compute two different slenderness. One is based on the entire column length, and the other one takes into account the distance between the connectors. Then you mix the two, introducing the number of shafts as well as the connector types through the neta factor. And at this point, it's the same process as before. You compute a relative slenderness, a Kz, and a Kc, and you have to retain the minimum of the buckling coefficients. And often it will be the behavior about the z-axis that will be driving the design. And to check the load on the connectors, we compare the design shear force on the connectors with their shear resistance. Keep in mind that advanced design will not be able to return the shear resistance because that would require some additional information about the joint, like nail diameter, for example, which we don't have yet. But it will return the shear force on the connectors, the FV force, which depends on the distance between the connectors, the spacing between shafts, and the VD shear force, which depend on the compression in the column and which is distributed differently depending on whether you have 2 shafts, 3, or even 4. Let's see how it works in advanced design. So let's work on this timber structure for a moment. I will select the front columns and I will turn them into spaced columns. So they are made of solid timber. And in the section type, I will choose the new spaced shaft entry. So I will use 2 shafts with 122 millimeters and 36 for the width and 36 as well for the spacing between shafts. Then, because I have vertical elements, they are identified as spaced columns. So I will define the distance between the connectors, the length of the unrestrained bay to be 68 centimeters, and the type of connectors. So if you have a drop-down list, I will go with nailed packs, and that's pretty much all I need to care about. The buckling length will be automatically computed, and I just need to run the calculation, get the internal forces. Once the calculation is done, I can select my columns and run a timber design sequence on selection and check the results graphically or in the shape sheet, the simplified version, for example. And you see we've got the actual load carrying capacity verification according to Annex C and the shear force on the connectors. You can choose the detailed report if you want to track every single value from this check. So if we comment on these results, we can see that the detailed report gives us the buckling coefficients in each plane, with KCZ being dependent on the lambda1 slenderness, which is based on the distance between the connectors. And also we've got the connector types, which in turn gives us an effective slenderness and a very small buckling coefficient that is actually driving the design and giving us the utilization for the actual load carrying capacity verification. And then we've got the shear force to properly design the connectors, with the distribution formula being the one for the two-shaft configuration. When it comes to space beams, they are commonly used as rafter ties and collar ties. And for the design, we've made adjustments to the various parameters, starting with the moment of inertia, because as we've seen before, there is one bending plane where the spacing between shafts will have an impact. We've made similar adjustments to the depth factor, KH, especially when used in tension verification, because there H is replaced by B, and in this case we are considering the width of a single rectangle. Now for the critical bending stress, where we use the alternate 632 equation, we are considering again the dimensions of a single rectangle. And then for the K-shape factor, which is used for torsion checks, we are considering a single rectangle. But then for the effective widths used in shear verifications, we are considering the two shafts. The results will be similar to what you would have for a single rectangle, except the design parameters are adjusted accordingly to account for the various shafts and the spacing between them. So moving on to the notch beam verifications. So in AD 2024, we've introduced the verification of beams with a notch on support with two configurations. The notch can be on the same side as the support, or it can be on the opposite side. And when it's on the same side, there will be a stress concentration at the notch corner, which would be around there. And this translates into a KV reduction factor, which will affect the shear resistance of the member. So when it's on the opposite side, well, there is no stress concentration and KV has no effect. But when it's on the same side, then KV may be smaller than 1, reducing the shear resistance. So this KV factor will depend on the depth of the beam at the support location, but also on the distance between the resulting support action and the notch corner, as well as the inclination of the notch, if there is an inclination at all. So let me show you how it works in advanced design. And for that, let's get back on our timber structure and we will focus on the platform that we have here. And if I were to define a notch on this beam, on the end of this beam is 75 by 225 millimeters. I would find the notch parameter there, so it would be a notch at the end on the same side of the support. The beam depth will be 150 and the distance to the notch corner will be 100 millimeters, and it will be a straight notch, so not an inclined one. And from there I can run the steel design on the selected beam and check the results either graphically or through the shape sheet. So it will be a strength verification right there, shear notches. So at the end of the member, formula and the utilization. Of course, you may prefer the detailed version of the report for information about KV here, which is smaller than 1 and which is reducing the shear resistance. Another verification introduced in version 2024 is compression perpendicular to the grain, and this is basically a support bearing verification at the end of a beam. So it's using the support action and the contact area. So the contact area is the support width, which is extended by 30 millimeters on each side, assuming there is enough distance for that. See, if you have a very short overhang, you won't reach the extra 30 millimeters. So in advanced design, you will define support width, as well as the potential overhang. And advanced design will automatically compute the KC magnification factor. It's not a reduction this time, because the capacity is in fact larger when you're dealing with local pressure on a small surface. And this effect is even more favorable for glue laminated timber than for solid timber. So let's see how that works in advanced design, getting back to our platform. And if I were to activate this bearing verification for this beam at the end of the member, I would activate this option there, define a support width of, let's say, 50 millimeters with no overhang, and then run the timber design. And I could check the results graphically or go straight to the simplified shape sheet to get the verification on the end support with a 13% utilization. And of course, I will get more information like the effective contact area here for the end support, the magnification factor, which is the one for a solid timber, and the final work ratio. And finally, we've got an improved optimization process, which will now consider also the deflection results. So this is an option to activate. You can also define the increments on the dimensions of the member. And in the optimization table, you will be suggested more appropriate and bigger sections if the deflection check is failed. So in the Eurocode 5, there are several deflection values to check, and activating this option ensures that none of this deflection will exceed the limit values that you can find either in the base text or most probably in your local appendix. So let's see how that works in advanced design. So back on our platform, we can select the beams, make sure that the deflection limits are properly defined there, and also that the corresponding option is activated in the optimization sequence. And run the timber design owner selection and check the optimization table. Of course, we can group the results based on names, and here the deflection check is failed, and therefore I'm suggested bigger sections. I realize I'm set in centimeters. I should probably switch to millimeters. Then you would accept the solution and update the results to get the updated deflection work ratio. So this concludes our presentation together with the new design for spaced members, spaced columns, but also spaced beams. We've seen the new verification for beams with a notch on support, also a new check for the compression perpendicular to the grain, and finally our improved optimization process, taking into account now also the deflection results. So keep in mind that you can now submit your projects for the upcoming Advanced Design Award. So be sure to check our website, advanceddesignaward.com. And well, I thank you all for your attention, and I hope to see you soon. Bye, everyone.
Right, so hi everyone, and thank you for attending. I'm here if you have any questions. Place them in the chat. We've got a question about this presentation only being in English now. Yeah, indeed. Today there is a mix of presentation in English and in French. And I think this one was not it was not translated, it was not adapted for the French market. Maybe it will come later. At a later date, it will be, maybe I can do that in French, it depends. We will keep you updated on that one. Indeed, it would be nice to have it in French as well for our French users. Right. So there doesn't seem to be any other questions. So I will end the recording now. So again, thank you all for attending, and I will see you soon. Bye.